Hello, today we continue our study of the Wilsonian view of renormalization. So last video we discussed what happens if you start from a microscopic system and you do what we call coarse graining, which is looking this system at bigger and bigger distance scales. That means smaller momentum scales, right? You're going towards the infrared and exchanging these microscopic, complicated microscopic interactions by some field that encapsulates the main properties of the system that manifest at lower momentum scales, and that mean bigger distances, right? And then we translated that idea to quantum field theories and got to the momentum shell integration idea, which I have right here, right? So the idea was to take the path integral that we usually have in quantum field theories, right, and limit the Fourier modes, right? So this phi here is the momentum space field, right? But I'm limiting how high the momentum can go, right? So I'm only integrating in momenta up to a physical cutoff scale above which the model I have encapsulated in this action right here is not valid anymore, right? And then I divide this integral into two parts, right? So I take a shell in the module of momentum, right, which lies between b lambda and lambda, right? And I call these modes that exist in that interval of momentum phi hat, right? Then I can separate the action in these two parts, the part that only involves phi, which is now limited to momentum smaller than b lambda, right? And the part that involves both phi and phi hat, right? And then I can integrate in phi hat. That leads to Feynman rules for phi hat, right? I can do these integrals and then show that this is equivalent to interactions. That then I can take this part here, write it as an exponential and put it together with this action so that I have a new path integral now that is limited to a lower cutoff. Right? Since this is all the same theory, right? We know that the low energies below these cutoffs, right? They should give the same results, right? After all, this is just equation, right? But somehow I have encapsulated the effect of the high momentum modes, right? The phi hat, back into my action. Right? Since now I'm only integrating up to b lambda, the effects of the modes above b lambda and below lambda should be included in the coefficients of the Lagrangian that is here. So I have the same theory, but the information about the UV modes is stored in a different place in this theory. Right? So today we want to refine that idea. Right? We're doing these shells, this shell integration in a more continuous way. Let's see how we can do that. The first step is to notice that it is a little bit awkward to have these cutoffs different in each version of the theory, because then if I want to compare what I'm calculating here and there, right, I have to actually do the loops and see that one of the loops goes up to one cutoff, the other one goes to a different cutoff, and then I have to compare the results of these integrals in order to have all the information, right? And it would be nice to be able to include everything in the Lagrangians, because then I just have to compare Lagrangians, right? Luckily enough, there's a trick that we can do in order to put back even the information of the cutoff into the Lagrangian. Right? And essentially what we're doing is zooming out or in, right? Changing scales. So we can do, after momentum shell integration, we can do the following scale transformation. So I'll take my momenta and redefine, right, in this way. So I just divide all the momenta by b, which is equivalent of stretching distances, right, by B. This B will be the parameter of my scale transformation, and not by chance. I'm also choosing this B to be the same B that I use in the shell integration here. And that is for the simple reason that doing this scale transformation will make my previous variable, K, right, this variable right here, that is limited to this momentum interval between 0 and B lambda, right? The new one will be now limited to this region between 0 and lambda. That means that this theory on the right here, written in terms of K prime, right, will have the same cutoff that this one has in terms of K, right? And then I can have all the information, right? Since the integrals in position and momenta are here in the action, right? Now I just threw all the information back into the action, and I can just compare actions, right? So these scale transformations are useful for us. So now what I'm, again, remember what we did last time? We were talking about lambda phi 4, right? And we got an effective Lagrangian, which was given, in fact, the effective action in this case, was given by the integral of the effective Lagrangian. And this was the integral in d for x of half of 1 plus delta z. So now I'm calling that those corrections that came from the integration out of the phi hat modes delta something, right? So this is what came, this is the new part which gives us the difference between S and S effective, right? So let me write all the terms. So this is the correction that can happen to the kinetic term, del mu phi square. And now I'm using definitions for these changes, which are closer to the ones we had in the previous renormalization scheme with counterterms, right? Then you had a mass term, which I call m0 square, and a correction to that, which I called in the previous video, I just called mu. Now I use a better notation for it. I'll call this delta m square, right? Phi square. Then we had the interaction itself. So the original term in the Lagrangian was this. Then we got a correction, exactly this one, right? Once we integrated that, I called it zeta in the previous lecture. Now I use something more intuitive. I'll call this delta lambda, right? Phi 4. And we even had more terms, right? In the original Lagrangian, we only had the kinetic, the mass, and the phi 4, but we saw that once we integrate out phi hat, we also get other contributions. And since these are essentially, I started from the original Lagrangian, there were 0, but they got correction, which we'll now call just delta C for the del mu phi to the 4th correction, plus delta D to the phi to the 6th correction, and so on and so forth. I have an infinite number of operators that I could define here. These names are not important because I usually bunch all these other operators together, right? And so everything in red here is the contribution of this out integration of phi hat. So this is our effective theory. One of the things that I want to do right now is to generalize these a little bit to d dimensions, right? We did everything in 4 dimensions last time, but the advantage of doing d dimensions in what follows is that this lambda phi 4 theory changes behavior around 4 dimensions. So if you do more than 4 dimensions has one behavior, less than 4 dimensions it has another behavior, and at 4 dimensions is even another behavior. And that's very useful because now we can do d dimensions and see all these behaviors just by changing d, instead of having, we can stick with lambda phi 4 and see many behaviors instead of actually looking 3 or 4 different models, right? Lambda phi 4 is very rich around 4 dimensions, right? So we'll generalize our results to d dimensions because we can play with d later, right? So this is the effective Lagrangian after out integration of phi hat. Now I want to do the second step, right? The scale transformation. Let's see what happens here, right? So now I'm making, since everything here is in position, what I'm really doing is this one, but you can see how they are equivalent, right? I'll just exchange x by x prime, right? So everywhere I have x here, I'll have to divide by b, right? So I have essentially to look for coordinates, right? I have some here, I have the derivatives here and here, and do the scale transformation. The first term comes from the integral itself, right? So I'll exchange x by x prime, and immediately I get, I have to divide by d powers of b, right? To move from x to x prime. Let me write it here so people have a place to look, right? So what I'm doing is x goes to x prime, and that means that I do this substitution in the integral, right? I exchange x by x prime divided by b. So here I have b powers, d powers in the denominator, so I'll have a b to the power minus d, right? And in the rest of the Lagrangian, I have to look for things that depend on the position. So here I have two derivatives, right? So now the derivatives are in x prime. Let me indicate that by derivative prime, and again I get some powers of b here. In the derivative, x is in the denominator, so here I'll have a b square, right? It goes into the numerator. Nothing changes in this part, right? There's no dependency on x, neither does here, right? In the case of these terms here, now this part has derivatives, right? So I have to put a derivative prime here and get a power of b to the fourth. That goes, oops, it's hard to write a b to the fourth, that goes here, right? And so on, right? You see that at every operator, I just have to put b to the number of derivatives, and I have an overall b to the minus d here that comes straight from the integration in x, right? Now you see, this is the kinetic term of my theory now, right? I can put this b multiplying here, right? And it's not normalized in the way we like, right? Remember that the whole point of the renormalization we did on the counterterm approach, right, was the whole point was to get rid of these field strength normalization here, right, and make the kinetic term and thus the operator, the propagators, properly normalized. I want the numerator of this propagator to be 1. And it is not, right? If I invert this operator here, I know that the numerator will have powers of b, this 1 plus delta z, right? This is essentially the z, and I want this all to be 1. And we know how to deal with that. Now we just renormalize the theory in the usual way. The first thing is to redefine the field, right? So I'll do this definition of a phi prime, right? Which compensates for all these factors here, right? So I just have to put a b to the 2 minus d, because I have to multiply this guy inside here, right? 1 plus delta z. of course, to the power half, because I have two powers of the field here, right? Phi. If I substitute this here, I'll have a canonically normalized kinetic term for this field phi prime. Right? And then I have to propagate this change everywhere, right? Here I will also have this thing to the power 2, right? In front of this guy, to the power 4 in front of this guy, and then I can redefine these things that appear, for instance, in front of the phi 2 square term as the new renormalized mass, right? In the case of the mass, it's easy to see what happens, right? I just define m prime square. Eventually I'll get rid of all these primes, right? But for now, let's keep them there. It's m prime square, right? Which is defined by this piece times also the part, because I'll have to exchange phi by phi prime. So there's also this thing, right? That goes here. But I have to be careful with the powers of b. There's also b to the minus d that goes all the way there, right? So in this case, the d goes away. This is a minus 2, right? Because of course I'm doing the invert of this transformation. So I'll just use that phi is b to the d minus 2 over 2, 1 plus delta z to the minus half phi prime, right? That's what I substitute here. So I'll get this d here over 2 cancelling with the and then of course this will be to the square, so there will be no 2. So the d here will cancel with the d that comes from outside, right? And I'm left only to b to minus 2, right? Because again, there's not this 2 is phi squared that I had here, right? And this is all this guy is to the power minus 1. So let me just reorganize this, because I want this b to be up front here, right? And of course I have m, no, there is no m, right? This is the m prime square. And I can continue doing that for every other coefficient here, right? Never forgetting the b to the minus d that goes inside, and this term right here to some power, the power of the field that appears there, right? Also, in some cases, I have even more powers of b because of the derivatives, right? So that, let me just write some of these definitions here. Let me bring these down here, put that in a different color. So this is just a reminder for us of the power, what happens with the field renormalization. And let me write the other terms. So there'll be a lambda prime that is defined by lambda 0 plus delta lambda times 1 plus delta z to the minus 2, because there are more powers of the field there, and b turns out to be d minus 4. So you can check, right, carefully each of these calculations. C prime will be, now in the original Lagrangian, I had c equals 0, but I want to be a little bit more general now, right? So I'll put a c plus delta c, right? So in the Lagrangian we started last lecture, this was last video, this was 0, right? But of course we saw that moment we integrated out, c became different from 0. And that means there was not really a good ansatz to start at that cutoff with c equals 0, because, you know, you could think of the ultraviolet continuation of that theory we started with. And once you did the integration out of that ultraviolet continuation, you would produce a c. So the most general thing is to start with c different from 0, and that's what we're doing now, just to keep it more general, right? So now I have a c here, right? And the redefinition will be this one, again, because in this case I have 4 powers of the field, but because of this b to the 4th here, I just have b to the power d, and we can go on, right? Let me write the last one, just because I wrote it there. It's the same story with the c. I can put a d, I start with a d different from 0, it's more general. I can always take this to 0, right, as my boundary condition for the start of this process later, right? And this is delta z now to the -3, because it's a phi to the 6, and this will be b to 2d minus 6, and so on, right? So it's clear that I have I can redefine all these guys easily by doing this process, right? What happens to the Lagrangian now, right? So now my Lagrangian, my action, will be given by this integral in dx of the L effective, right? Now it's just written x prime half of del mu prime phi prime square plus half of m prime square phi prime square 1/4 lambda prime phi prime to the 4th plus c prime del mu prime phi prime to the 4th d prime phi prime to the 6th, and so on. So you see what we did here. We included both the effect of the out-integration, which is encapsulated in all these deltas here, and the rescaling, right? This stretching of our space-time that is totally equivalent to changing the UV cutoff, and is encapsulated in these powers of b here, in the coefficients of my Lagrangian, right? These coefficients that are called the Wilson coefficients of my theory, right? Which is nice because now we have a Lagrangian, right? Which is composed of these operators. And remember, the operators that are appearing in my Lagrangian or not, they carry 2 pieces of information. One, what degrees of freedom I have, or what degrees of freedom I put in my model, right? And the symmetries, right? The symmetries forbid some operators, allow other operators, and that's all in the operators themselves, right? The symmetries. But the coefficients now carry the information of how I'm including in my theory the effects of the UV degrees of freedom, right? The high frequency degrees of freedom is all encapsulated. And if I can include that into the loops or my coefficients, right? But I decided to put in the coefficients, and that tells me how the theory behaves at different scales, right? Which is a really nice way of encapsulating that information, right? So what we're seeing here is that by doing these 2 transformations, right? So let schematically see what we did, right? I start from a Lagrangian, right? Which can be written in terms of these 2 different degrees of freedom, which now are the high energy and low energy degrees of freedom, right? What we have in mind here, remember, just to keep everyone on board, right? We had in mind this separation of scales, and again, remember really the low scale is limited by the mass of this guy, because below that I don't see these particles, make not much sense to describe the field if below that mass, right? And I divided these into phi and phi hat, right? And now I did 2 operations, in fact 3, but one of them is implicit, right? I integrate out phi hat, and I rescale, right? I do a scale transformation, which can be thought of this in momentum space or this in position space, right? And the third implicit operation is that I renormalize, so I keep these properly normalized. That's why all the other Wilson coefficients change, but not the kinetic one. I keep my propagators always normalized so they don't change, right? That's the hidden one, right, that I do at the end. But then I get these effective, these effective Lagrangian in terms of these new variables, right? Even the position is x prime, but then I'll drop all the primes because I don't need them, right? The joint effect of these two explicit transformations here, plus the renormalization, right, can be thought of as a transformation in this space of Lagrangians, right, in which I have all the Lagrangians that have these same operators, which means, again, same degrees of freedom and same symmetries, right? Every time I do a transformation like that, I connect a Lagrangian in this space to another Lagrangian in this space. And these transformations, the set of all transformations that do that in the space of this particular Lagrangian is called the renormalization group of these Lagrangian, right? It's not really a group, and you can see why, right? These transformations of Lagrangians, they satisfy most of the group properties, but the transformations not always have an inverse, right? And that's important, right? You can think of these transformations, right? We said it before, as throwing away information from the UV. I'm starting to lose the detailed microscopic interactions. So it's easy to guess that sometimes two theories which have different behaviors, when you take into consideration just the details in the microscopic version of the theory, might, once you lose that detailed behavior, they might become very similar or even the same. So integrating out degrees of freedom is really well defined, but if you want to go back, that's not always possible, right? In fact, in general, it's not possible. Just by knowing the behavior at long distances to guess the behavior at short distances, right? So this is not really a group, but historically it was called the renormalization group, right? The set of all transformations that do that. So now I have this idea that I can move between Lagrangians with this parameter b, right? That's the parameter of my transformation. It enters both in the integration out and the rescaling, right? I can go between Lagrangians that live in the space of all the Lagrangians that have the same degrees of freedom and the same symmetries, because I would never produce operators that violate that symmetry, and I would never produce new degrees of freedom just by doing that, right? We can do more complicated stuff, like I don't know, an anomalous symmetry could appear, right? Once you do that, you produce, if the symmetry is not respected by your quantum theory, you can produce terms that violate that symmetry. You could think of getting bound states and then rewrite these bound states in new fields that are equivalent to that bound state, but that's not what we're doing here. In this case, I'm just connecting Lagrangians that all have the exact same operators, right? And now I can even go further, right? This is like the discrete version of this group, but I can take B. Remember, B is smaller than 1, But if I take B as close to 1 as possible, right? Now I can start moving between Lagrangians that are arbitrarily close to each other, right? And do a continuous transformation in this space of Lagrangians, right? Now what I have in mind is this, right? I have some space, right, in which the coordinates are the Wilson coefficients, right? I have an infinite number of dimensions in this space, right? I won't draw all of them because I have this problem with drawing anything bigger than three-dimensional. Even three-dimensional is sometimes hard for me, but four-dimensional is totally out of my capacity, right? So I'll just draw 3 of these Wilson coefficients. I choose the mass, the lambda, and c, right? And now what I'm doing is when I'm moving, right, in the limit where b is very close to 1, right, goes to 1. From below, right, b is always smaller than 1. Now I have transformation that takes me from some Lagrangian to another one. I just walk through this space of Lagrangians and get to a second one. Let's call that L prime, and I continue doing this integration of shells with infinitely small I don't know how to call that, infinitely small size, right? Let's say, and width, right? And you go to L prime and then to L3 primes that I indicated there. And the important thing to notice is that this transformation always go in the direction of a theory that is valid up to a higher cutoff. So let's call that a UV theory, where you still have UV degrees of freedom, towards one that is really the cutoff is lower and lower, right? Now this is translated of a stretching of spacetime, but that's the same, right? To a theory that is valid to smaller and smaller energies, right? I'm calling these the IR theory, right? So we call this the renormalization group flow. It's really this trajectory that is going on here. And what it tells me is, as I do these renormalization group transformations, how the parameters in my Lagrangian are changing, how I'm moving through this space of Lagrangian, right? So any point in this multi-dimensional space will be a Lagrangian with the exact same operators, but different coefficients, right? So now my transformation operates in this space. There's a few special points here. One of them is clearly the origin, right? So the origin of this space is what I call L0, right? And that's a free, in this case, massless scalar theory, right? The only thing that survives there is this term right here. Every other term is 0, right? This much is clear. And that's a free theory for a massless scalar field. Along the direction of the mass here, I have still a free theory, but now with a mass, right? And I have some region that I could define here, right? It doesn't need to be a sphere, but I won't be able to draw anything but a sphere. Let me just make it a little smaller, put the center there, right? There's a region around this point where all the Wilson coefficients are small in some sense. If I go too far away from that point, one of the Wilson coefficients, or all of them, can become large. So this region around L0 is the perturbative region, right? Even in the sense of the mass is perturbative inside that sphere, right? So I have the free theory of the origin, and I have some region around that origin, which is where my perturbative expansion is valid, right? And you can see that since all the corrections, right, all the loop corrections that introduce these deltas here, right, all these deltas are proportional to some power of the interactions in my theory. All these Wilson coefficients from these down, right, are interactions, and if I turn off all the interactions, all deltas go to zero, because then there's no loops, right? There's nothing, it's just a free theory. So you can see that close to this point, right, my coefficients will change really slowly as I pass close to this point, and at this point they won't change at all. In a free theory, there's no corrections, right? There's nothing to integrate out. I'm not doing anything, right? And that's what we call a fixed point of my transformation, right? In that, if my trajectory happens to go to that point, once I get there, I stop at that point, because now every transformation is leading me to the same Lagrangian again and again and again, right? That's a very trivial fixed point, because it's a stupid theory. I would never really bother studying too much a theory with no interaction, right? But it is an important fixed point, because if you go close to it, right, if you're near that point, you have some very particular behaviors of your theory. In particular, your theory starts to change, almost not change, as you move between scales, right? Your trajectory, this piece of the trajectory, right? There's no way of indicating that in the plot, but you could put more arrows here, in the sense that consecutive transformations, let's make B not so continuous, right? So we can have steps, right? Consecutive steps will be really close to each other near this region, right? And really far from each other. So a step here could take you directly from this point to this one, but near this fixed point in the origin, right? They are really close to each other, because all the couplings are small, so the corrections, right, will be small too. So near this fixed point, the theory flows slowly. That's one way of saying it, right? And this is called the Gaussian fixed point, for the simple reason that a free theory only has phi square terms, right? So your action is a Gaussian, right? So it's easy to integrate. The exponential of your action will be just a Gaussian, and that's what we know to integrate. And so Gaussian in the context of a field theory is just a free theory, right? That's what that means. So some places you see this called the Gaussian fixed point. In other places will be called the free theory fixed point. One common way that you'll see these renormalization group flows indicated graphically is by a set of these trajectories, right? Because if you start from different starting points, these trajectories can go to different places, right? So I can take a set of initial points here and indicate the trajectories like that, so you can see what the trajectory is doing everywhere, right? You can see what happens everywhere in this space. Sometimes they will be, as I said, since this is not inversible in all cases, sometimes there will be converging points there where many theories flow to the same infrared one. Remember that these arrows are always from UV to infrared, so you see pictures like that in any book discussing renormalization flow, right? And that's what it means, right? You have these families of curves which are Lagrangians with the same degree of freedom, the same symmetries, but you started from a different boundary condition at the UV, right? And that leads to different Lagrangians at the infrared. What is important is that Lagrangians that belong to the same trajectory, they are the same theory, right? I'm just putting the behavior of the UV modes back into the Wilson coefficients or not, right? That's what different points along the same trajectory mean, right? And so that's a common way of indicating flows. So now let's try to get the bigger picture, right? And compare this view of renormalization to the one we had before with the counterterms. So let's call method 1 the BPHZ renormalization, the one with the counterterms. What did we do there, right? So I took a Lagrangian. Say, I'll just use lambda phi 4 as an example, right? Which was this, right? In this case, I call this the bare mass and the bare coupling constant, right? And then I used, innocently, this Lagrangian to calculate some endpoint functions. So I just took this and calculated some green functions in this theory, right? Which then I can translate into matrix elements and cross sections, right? In this case, at leading order, there is just no information about the UV modes, right? I'm just, the excitations that appear here at 3 level are only containing the information about whatever external moment I'm putting here, right? But they don't include any knowledge about what happens in the UV of this theory. That means that once I include the next to leading order correction, any loop, right? And that also applies to next to leading order, next to leading order. So let's call that n plus leading order, right? Could be n leading order or higher, right? Once I do that, right, I'm including all the UV behavior in one swoop, right? I just put a loop there and suddenly all that sensitivity to UV enters. And that causes a big change in my Wilson coefficients. That's what's happening, right? This big change will be even bigger if I decided that this theory is valid up to arbitrarily high cutoffs, right? If I integrate my loops to infinity, right, then the change in those Wilson coefficients will also be infinite, right? And now it's not impressive, right? It's not even surprising that I got a diverging correction to these guys, right? The infinity I'm getting out is the infinity I put in, right? The moment we want this theory to be valid to arbitrarily high cutoffs, I'm saying the correction to my coefficients will be also divergent, right? It's just, once you realize that, that's the beauty of the Wilson approach, right? Once you realize that, you see that what you were doing back in this previous method was starting your renormalization flow trajectory at an infinitely distant point. And then you get surprised that you got an infinitely big correction to come to the low energy theory, right? But in any case, we found a way to deal with that, because then you take this apparently infinite green function, right? And you renormalize, right? Getting a new Lagrangian. Let me write the new Lagrangian. Let me just prettify stuff, right? I get now a new Lagrangian. which has the properly physical and finite Wilson coefficients. So the mass, right? I can take the renormalized mass to be the pole mass, the MS mass, doesn't matter. The important thing, this is the finite number now, right? Lambda, the same for the couplings. But of course, now I have the counter terms. Counter terms, right? And this now has, the important thing here is now, if I want this m squared, for instance, to be finite, right? These I define like this, right? In the case of lambda phi 4, right? I need, this correction will be divergent, right? Because of this integration up to infinity, right? And that means that my starting Wilson coefficient also needs to be infinity, right? So that's just a consequence of my choice. But then I get a finite number and finite predictions. If I look at anything that can be measured and calculated with the inclusion of the counterterms that will solve the divergences I introduced, that's the important point, right? I'll get finite predictions and everyone is happy, right? So this is method 1, is the BPHZ renormalization, right? Now, speaking like that, it sounds really stupid to do things like that, right? All you have to do to avoid this completely is to give up this condition that our theory is valid up to arbitrarily large energies, which we have no indication, right? There's no scientific reason to believe that, right? You can, I mean, you wish, maybe you wish that is true, but there's no way of testing that, right? So it was just an assumption we made, right? If you give that up, you don't need to do any of that. But on the flip side, right, this is the easiest way of doing it, right? This momentum shell integration in practice is very hard to do for calculations. So you see that being used a lot, right? No problem there. You get finite predictions. In fact, this method and the other one need to give the same predictions. This is operationally way easier to do, and that's what we do it a lot. The reason this understanding is important is that now you can stop worrying about the infinities, right? You can stop worrying about these diverging integrals because they're only diverging because you're doing this, right? And now you can think this as an approximation even, right? You say, well, my cutoff is high. I'm doing the theory far from that cutoff, right? So I can take that cutoff to infinity, right? With no problems. It's just an approximation. It's far enough that I can take it to be infinite. As long as you don't believe it is infinite, then you understand that all these divergences that are appearing in your theory is just a artifact of this approximation. You throw in the cutoff to infinity, right? And you're fine. You're concealing these by treating this approximation properly. That's one way of interpreting the counterterm version of renormalization, right? Now let's go to method 2, right? Method 2 gives us is the Wilson one, right? It gives us a way better visualization of what is happening, right? But it's almost never used. That's the funny thing, because operationally it's very complicated to do for most theories, right? So in this version, you also start from the Lagrangian that we started before, right? So now this the mass and the coupling that you start with, still calling them M0 and lambda 0, but now Although some books still call these guys bare mass and bare coupling, even in this version, now these guys are not really bare anymore, because I'm assuming this Lagrangian has a physical cutoff, lambda. So these guys are already including whatever happens above that scale. And they are finite, right? You're starting from some number here that is valid only up, this theory is valid only up to some physical lambda. So whatever is going on above the lambda, I don't know which theory is valid there. Might not even be a field theory, but that's already encapsulated at these numbers at the start. But now you go away from that, right? You can move to effective theories valid at the lower and lower energies. So you're doing the renormalization group transformations. You're doing the renormalization group transformations, right? And what you assume is that you're working at energies really far below the cutoff, so that you can safely assume that the results do not depend on the position of the cutoff. But by changing the cutoff, you see, you put more and more the UV effects into effectively into your Wilson coefficients. They will carry that. As you do that, if you start with these numbers fairly small, let's now think what happens in perturbative theories. Suppose you started within that region around the Gaussian fixed point where everything is perturbative. These guys will change incrementally. All your loop calculations are finite now because there's a physical cutoff, right? And as you move through this space by doing renormalization group, these guys are always finite, right? They'll start changing into m and lambda, and now m and lambda change continuously, right? And you can even have some control when these guys, maybe one of them is growing, and you're going towards the non-perturbative regime where you have to stop, right? So you have a lot more of control, right? And you're exchanging this Lagrangian for that effective one. That is really those terms. Now I just rename those guys, right? So I'm calling 0 now, like this initial condition in terms of the normalization group flow, right? And you have every other operator, again, consistent with degrees of freedom and symmetries, right? So now when you calculate that endpoint function using this theory, right, this is already finite, right? Because a lot of the effects, a lot of the UV effects are already included in the coefficients. And even if you do loops, those loops will be a small correction, because the loop is really only integrated to some cutoff that is not, it's far enough to be independent of the cutoff, but close enough that the contribution of the loop will be small. We'll see more details about that. That has a lot to do with this size of these logs. I already hinted of something with the logs. We'll see that more with more detail soon, right? But the results are finite, and the beauty of this approach is that you don't have this impression that you're breaking the perturbative series, right? Even the loops are small as you add them up, the next to leading order, the next to leading order. You're always adding small contributions, not only from the point of view of the couplings that are small, but also the integrals are small, right? And so that's beautiful, right? The only downside of that is that this hard cutoff breaks all Ward Takahashi identities. Is a lot of trouble from the point of view of symmetries to do something like that. So mostly we use method 1. But you can always have in your mind that you're really doing method 2 in some not very good limit in terms of your intuition, right? You're throwing this UV cutoff to infinity, and that's why it looks like you're breaking everything. But we found a way already, right, of removing that divergence and having a well-defined perturbation theory, which is the renormalized perturbation theory, right? And so that's what we learn from the Wilson approach to renormalization. Okay, so this is all very qualitative so far, but there's a few important quantitative stuff that we can say about this renormalization group flow, right? At least for the scalar theory. Of course, once we want to do quantitative stuff, then we need to be on the perturbative region of the theory, right? And that assumes we're close, right, in this space, right? So the coordinates in this space of Lagrangians are given by the Wilson coefficients, right? And we need to be fairly close to the Gaussian fixed point, right? The closer we are to it, the better the approximation, the calculation we'll do now, right? And the thing we want to do is to go back to that expression of how the coefficients flow that we deduced up here, this one in the box right here. Let me copy it and go back to where we can write it, right? And we want to see how this behaves really close to that Gaussian fixed point, right? So now I want to see in the limit where this is true, right, that all these coefficients are really close to zero, how these transformations look, right? The field, by definition, right, this transformation of the field will be included in the others, right? And will the kinetic term will always be kept. The Wilson coefficient will always be 1/2, right? So we will only have to worry about the other ones. And the thing here is that all these delta terms, they are always higher than the leading term in each of these transformations in terms of the couplings, right? This involves higher powers either in lambda itself or in the other couplings than just a linear term in lambda. So what I'm doing here is that if I go really close to this point, I can linearize these transformations to only involve one power of the coupling. And here I'm thinking of m squared really like we do in the MS bar scheme, like a coupling, right? Just a 2-point vertex like that, right? In that case, it's easy. All I have to do is throw away all the deltas, right? Even products of deltas. And these transformations get a really simple linear form. So for m prime square is just m0 square b to the minus 2. In this case, lambda prime square, what square? No, I don't need that square. Lambda prime is lambda 0 times b d to the minus 4. C prime is c b to the power d, and d prime is d b to the minus 6, right? Of course, there's always order delta something terms in all of these cases, right? You see that at this approximation, right, you still need a coupling that starts different from 0 in order to generate the prime version of it, right? But this is basically dominated by the rescaling transformation, right? We're just seeing how these Wilson coefficients change as I change the scale in which I'm looking my theory, right? I'm changing the cutoff, but that has been translated to scale transformation now. And you see B is smaller than 1. That's the important thing to remember. So coefficients that have a negative power of B will grow as I multiply by B in each transformation step, right? If it's always easier to think in the discrete version, right? So every time I do a transformation, these guys grow, right? This one, for instance, that has a negative power of B. The other guys, right? If the power of B is positive, then they get smaller. So they diminish as I do the transformation. That means that, for instance, take the two clear cases here, right? So the mass is always negative, independent of dimension, and C, as long as I have positive number of space-time dimensions, right? This is always positive, right? So in the BC plane, right, let's take a look at the not BC, M square C plane, right? M square here, C here, right? You can see that in this plane, let me put the Gaussian point here. The flow will be in this direction, close to C. Remember, I can describe this as a set of all these curves going around, but near C, as I go from UV to IR, C will be becoming smaller and smaller. And along the axis of M, it will be growing. So you can imagine on this plane, and be careful with these lines in M. You could imagine, since you are in the M square axis, everything else is 0. What is the coupling that is making that change? But I'm not considering all the other dimensions here, right? So I could be just a projection on this plane, right? So other couplings could be different than 0 and forcing M up. The important point is that M is growing, and you can imagine that other curves will interpolate that behavior as I go close to these two extremes here, right? So that's how you can see the renormalization flow. Right? And now I have a classification, a clear classification that of course depends on the number of space-time dimensions, right? For some of these operators, so take lambda, this could be positive or negative depending on D, right? That's why lambda phi 4 is interesting near 4 dimensions, right? That's when the behavior changes, right? But now I have a classification of operators, right? Or Wilson coefficients, right? So I can say that when the coefficient grows, right? So let me put that the coefficient goes up as I go to the infrared, right? Those operators are called the relevant operators because they become more and more important away from the UV. So if you go back to this coarse graining idea, right? These are the operators that will describe they are relevant, right, for the long distance behavior of your material, right? Think again in terms of materials, right? The operators that have coefficients that grow as you coarse grain, right, will become the operators that dictate the behavior once you're not seeing the microscopic degrees of freedom anymore, right? On the flip side, right, the opposite behavior, coefficients that diminish as you do this coarse graining, right? They are called the irrelevant operators. Why? Because they encapsulate information of the microscopic degrees of freedom that becomes less and less important as you look at longer and longer scales, and eventually they don't matter anymore, right? So they become irrelevant for the long distance behavior of your theory. And the same is happening here in quantum field theory, right? The behavior of these operators that are irrelevant is becoming less and less important as you put information back into the coefficients. They become smaller and smaller. So that's the part of your UV theory that has no effect on the IR behavior of the theory. And of course, there's some coefficients that don't change, right? They are in the middle here, but they don't change in this approximation. It's important to see that I'm talking about an approximation here. So take lambda for d equal to 4. This b will disappear, and that means that lambda 0 is the same as lambda, so it doesn't change as I integrate stuff out. But there's also this part, right? If this is not creating any change at all, that means that the growing or the diminishing of lambda will be dominated by the next order correction. I cannot ignore this one, right? So we call these operators marginal operators. And marginal means they are, if they grow or if they either grow or diminish, right? But that's they do it slowly, because now you depend on the next order correction to their behavior. And at least for perturbative theories, this next correction is smaller than the leading one. So it will be a small effect in one of these directions, right? And we can see a few examples of that. Now is where lambda phi 4 shines, right? We can see just by looking at this that the mass term, right? So the mass is the Wilson coefficient of this operator. So this guy is always relevant, right? Because the Wilson coefficient will always grow, right? And the other operator, phi 4, right, can be relevant, irrelevant, or marginal, depending on the dimension. Let me copy this thing up here, right? That's how it behaves. So you see that for d smaller than 4, this guy is relevant. You get a negative power here, right? For d equals 4, this is marginal. You really have to look at the next order correction because b will disappear. And for d bigger than 4, this guy is irrelevant. And now we can look at these three cases. Just by changing d, we can see three kinds of different behaviors just looking at lambda phi 4, which is kind of neat, right? We'll do that soon, right? But before, let's now compare, right? Again, I'm always trying to compare the Wilson approach with this thing we did with the counterterms, right? The BPHC renormalization scheme, right? Notice that what is showing up here, right, is very closely related with the dimension of these guys, of these Wilson coefficients, right? This is the behavior under scaling, and we know the different physical quantities scale as a stretch space-time, depending on their mass dimensions, right? On how they, you can get that from dimensional analysis. So let's see what is the dimension of a Wilson coefficient. So now I'm thinking of a coefficient CNM, right? This is a Wilson coefficient. It can be lambda, it can be the mass square, it could be any of these guys, right? And N and M indicate, so this guy, I'm just constraining myself to scalar theories here, right? So n means that you have n powers of phi in the operator that this coefficient multiplies, right? And m is the number of derivatives. Right? So you can see that the scaling, right? If you go back to where we deduced these powers of B that appear here, right? You can see that there's always a power of B that comes from the integral, right? We did a few minutes ago. So there's a B to the minus D, which is just the measure of integration in position, right? There was another one that came from the transformation law of the field, right? The field transforms as B to the D minus 2 over 2 phi prime. Remember? Now I'm throwing away this delta Z part, right? Because I'm doing this approximation where I'm really close to the Gaussian fixed point, right? If I have any n powers of phi, that means that I'll have a power of B here that is D minus 2 over 2 times n, because I have any n powers of the field. And of course, if I have derivatives, I have del x, right? I have this x in the denominator. So when I scale with B, I'll have a B in the numerator. And if I have m derivatives, that will give me a B to the power of m here, right? So just thinking of how these coefficients transform under scale, I can say that a Wilson coefficient transforms in this way, right? In the same approximation I did right here. And you can check that expression for all these guys, right? Just figure out how many derivatives and how many powers of the field each of these, the operator that is in front of this, is multiplied by these coefficients, has, and you can check that expression for all of these guys, right? But now, let me just rewrite these in a compact way. You see that this is B to the power n D minus 2 over 2 plus m minus D, right? D here is always the number of space-time dimensions, C and m. So this is how all Wilson coefficients transform, again, in this approximation, right? But now, this is, you might be already recognizing this part of this coefficient, really, right? This is the exponent, right? Because the dimension of an operator with n powers of a scalar field and m derivatives is exactly n D minus 2 over 2, right? We saw that a few videos ago. This is the dimension of a scalar field in D space-time dimensions, right? And I have n of them, plus m, which is the dimension of m derivatives, right? I'll call this thing just D and m, right? D and m. The little d here will be the dimension of the operator, right? It's important not to confuse the dimension of the operator with the dimension of the coefficient, right? And that means also that I can write this expression again in this way. B is equal to B D and m minus the space-time dimensions C and m, right? But now this, as we know, right, the sum of the dimension of the coefficient with the dimension of the operator, so the dimension of C and m plus the dimension of O and m is equal to the number of space-time dimensions, because, I mean, the action needs to be adimensional, right? And that means that this thing that is appearing up here is really the dimension of the coefficient, right? It's just this one minus this one. It's actually minus the dimension of the coefficient. So this is B2 minus the dimension of C and M itself, C and M. So you see, the coefficients are scaling according to their dimension. This is important. Let me put it like that, right? So now, this is really cool, right? Because if this thing is positive, let's say, let's take the three cases, right? This can be positive, negative, or zero. Now, let's say the dimension of C and M is bigger than zero. Right? That means, according to this classification, right? The one here, right? Either the coefficient grows, diminishes, or is zero at this approximation, right? We would say if it's relevant, irrelevant, or marginal, right? This means that this guy is relevant, because now you have a negative b to a negative power, and that means it grows. Right? But that criteria we saw back when we doing counterterms, that having the dimension of your Wilson coefficient, we were not calling them Wilson coefficients back then, but we were calling them couplings, just couplings, right? Means these guys is super renormalizable. So as I go down in scales, right? As I integrate out UV scales, my super renormalizable coefficients will become more and more important. Right? Second option, I can take this guy to be marginal. That means that this dimension is zero, because then the power of B goes away. So these are the marginal operators. Right? Usually you use marginal and relevant to operators and also these two operators, but we're abusing that and talking about the coefficients, which are easier to look at, right? So if this is zero, this is a marginal guy. But again, if you go back to the video with the classification, these are the renormalizable operators, right? When the coupling is adimensional, right? You have renormalizable interactions. And then finally, if you take the dimension smaller than zero, right? These are irrelevant because they get smaller and smaller as you integrate over the UV, and these are the non-renormalizable interactions, which is beautiful, right? As you go to higher and higher distances, right, your non-renormalizable coefficients become less and less relevant to your calculation. Right? Not surprisingly, another way of getting exactly the same conclusion comes straight away from dimensional analysis, right? So we know that these Wilson coefficients, right, in natural units, they have a dimension of some mass scale. I'm putting mass here, but it's not really the mass of the particle, it's some scale of mass, right? To the power of their dimension, right? Actually, that's the definition of their dimension. So this is trivial. The point is that what scale naturally appears here? Let me write this more explicitly, right? So I'm saying this is D minus D and m, just to express this in terms of the dimension of the operator. This is the dimension of the coefficient, right? But what mass scale should appear here? If you think that this coefficient is always obtained by integrating out a slice right above some cutoff, right? When you integrate that, this loop integration involves these lambda and b lambda that are in that step of the momentum shell integration, right? So the size of this guy will receive a contribution that is of this lambda to the appropriate power of this guy should have by dimensional analysis, right? So these Wilson coefficients will be naturally of order lambda to this power. And we saw an example of that when we calculated mu on the last video, right? We saw that mu was something like 1 minus b lambda square, right? B square lambda square. Which means that unless you take b really small, but then of course if you're doing infinitely small slices, this correction is infinitely small, but you have to think that then you have infinite many of these slices. But if you do a step, it's pretty clear that mu will be of the order lambda, because lambda is bigger than any other scale, right? The only exception to that, if there was some symmetry that was protecting this guy and keeping it small by a really small coefficient in front of that. This idea is what is behind the idea of naturalness that sometimes you hear, especially particle physics people talking about in relation of the Higgs, in relation to the Higgs boson and so on. Because you expect, since the contributions from this integration out of degrees of freedom is dominated by this UV cutoff, right? That the coefficients themselves will be of the size of the cutoff to the appropriate power that is given to you by dimensional analysis. Right? If that is true, if there's no symmetry taking you away from the naturalness guess that I'm making here, then you know that this coefficient will generate an interaction, right? At this interaction, you have a number of external momenta going in, right? And you can always write something like that. You take this power of lambda, the Feynman rule for the vertex will be proportional to 1 over lambda to dnm minus d. I just inverted here to put lambda in the denominator. And of course, whatever is the dimension of that particular endpoint function that you're using to calculate a scattering with this interaction, you can have some some powers of momenta outside, but you can put some powers here, right, and write the interaction in terms of this expansion, which means that for d and m smaller than d, right, and that means negative power here, and that means relevant and renormalizable interactions, right? These will be more and more important as you go to small momenta compared to the cutoff. And now this is physical momenta I'm talking about. This is the momentum that goes into the vertex of that interaction, right? So the relevant are, again, important, which is just a synonym of relevant, right? At low p, as compared to lambda, right? Now, if the dimension of the operator is bigger than your space-time dimension, right, then you see that the interaction will be suppressed by p over lambda to some power, right? That depends on how big this difference is, right? And this is suppressed. I think there's two p's here, not sure. I hope the English is all right, because I won't be able to spell check these, right? So suppressed by some power, right? In fact, this power of P over lambda, right? And this is the non-renormalizable interactions, the irrelevant interactions. Right? So from dimensional analysis alone and these naturalness criteria, I can tell that my non-renormalizable operators go away if I'm talking about a theory that I'm doing predictions and testing those predictions at a scale that is much smaller than the cutoff of the theory, right? So now all this mystery, right, behind renormalizable or even non-renormalizable theories, but as you might remember from the non-renormalizable theories video, that they are okay as long as you have some scale to suppress the interaction, so you can take a finite number of non-renormalizable operators, right? Now this mystery of why the theories that we managed to find for the physics systems we wanted to describe are like that, this mystery goes away, right? Because before we had this condition, right, that the theories that work, right, were either renormalizable or non-renormalizable, but with some suppressing UV scale. If you didn't have this suppression that goes with some power of the dimension of the operator, right, you couldn't ignore all this infinite tower of operators, right? Both this theory now arise naturally, as long as you are away from the UV cutoff, right? You can start with any theory with an infinite number of operators near the cutoff, but as you look at that theory far away from that cutoff, all the non-renormalizable operators are being suppressed more and more by this effect, right? So when you look at your theories that work, you only have a few operators, which are the renormalizable ones, right? As you go like in an intermediate region where you're going close to the UV cutoff, but not so close, then you start to perceive something like that. You have a non-renormalizable theory, but still you don't need those infinite number of operators. And of course, if you get too close to the cutoff, the whole thing breaks down. Even some assumptions we make here are starting to break down, and you have a problem, right? So this conclusion is important to emphasize, that this conclusion was made at a particular condition, right? We assume two things to have this conclusion, right? The first one was this was a perturbative analysis, right? So we ignore all those deltas or even took them as a small correction, right? And two, we started with a finite cutoff. Right? So these points are important, right? It's important to emphasize that, right? So because we're talking about perturbative theories, right? This is dominated by the scaling, right? In the case of marginal operators, I can take the next term and it will be small, and things will move smoothly, right? But that could all be reversed by strong interactions, right? So if at any point as I'm walking through this renormalization group flow trajectory, right? I'm walking through this trajectory. Any of these couplings get too strong, right? Then the next term, right, in delta expansion can become significant, right? And reverse the flow and then throw one of these non-renormalizable operators up, and then you keep going to the infrared. Now it can go anywhere, right? But at least for weak theories, and those are the theories that actually work, right? If you look at the standard model, the places where we actually calculate stuff is mostly perturbative theories. Then you're not impressed that we found perturbative renormalizable theories for everything, right? Weak theories behave like that. Now, just to have a concrete example how some theories behave, right, and how I have to be careful if my Wilson coefficients are going away from the Gaussian fixed point, let's look at how lambda phi 4 behaves in these three options, right? So let's start with the number of space-time dimensions bigger than 4, right? And then, as we have seen, right, lambda, the very lambda of phi 4 is irrelevant, right? And the only relevant Wilson coefficient is the mass itself, right? In that case, we have to start, right? Otherwise, nothing makes sense. I have to start with a mass, right? The M0, the starting point of my flow, much smaller than the cutoff, right? But as I integrate out UV degrees of freedom, right, M0 will flow and will become bigger, right? If I take n steps, let's call this n transformations, finite transformations of the renormalization group, right? This goes to a m prime square, which is m0 squared times b to the minus 2n, because I took n steps, right? At the same time, lambda 0 is going down to some lambda prime, right? Let's see how this behaves, right? I can make a plot where I put in this direction, right? I can take the renormalization flow trajectory and put here, right? So this is growing number of transformations, right? It's the flow direction, right? The direction along those arrows that I wrote in the renormalization flow. So this goes from the UV to the IR, right? The mass, let me put two colors, right? I indicate the mass in red here, right? And the cutoff in blue. As I go and do these transformations, the mass is going up, like b squared, right? And lambda is going down. So my theory in the infrared will always go to this situation where m prime square is close to m lambda square, against the natural value for this Wilson coefficient after integrating out UV is the cutoff to the power, the appropriate power dictated by the dimensional analysis of this Wilson coefficient. And that is always the trouble with scalar fields, right? It takes some and that theory I cannot work anymore, right? I cannot stay with a theory that the cutoff is right on the mass of the particle, because then any external momentum will go over the cutoff, and then I need to find the UV continuation of the theory, right? So the way to deal with that, right, is to fine tune your theory. So you have to imagine that this initial point was really close to, there's two ways of doing that. The first one, which is simpler, right, is to have M0 like amazingly close to the Gaussian fixed point. That way, the mass is stuck there. Remember, close to the fixed point, the renormalization flow goes really slowly, right? And in that way, now you can be really, let me do this properly, start to get lazy by the end of the video. So now the lambda is going down as I take steps, right? But M is basically not flowing at all. So I have a much easier way of going away from the cutoff and still having this distance between the mass of your scalar and the cutoff, right? And so that's one way of doing, but you really need to start close to that fixed point. The other way is to start away from the fixed point, right? The Gaussian fixed point, but in a direction in which the flow is towards the fixed point, right? So that first you run really quickly, right? But you then get stuck near the fixed point and you can lower your cutoff without increasing the mass too much. And so that's a thing that is always the case with fixed with mass of scalars, because the mass of scalars are not protected by any symmetry. You see that you could straight away think, well, the mass of fermions also has this problem. It's also a Wilson coefficient with positive dimension, right? But the mass of fermions is protected by the chiral symmetry, so it goes away from this naturalness expectation, right? So that's one of the things you can see for D bigger than 4. The next one is what happens with lambda phi 4 at 4 dimensions. Now I want to look at this one. Now the mass is relevant. Nothing changes there. It's the same analysis as far as the mass is concerned. But now lambda is also it's changing, right? It's not relevant yet, but now it has become marginal, right? We have seen this before. So in 4 dimensions, lambda is marginal. That means that I need to go to the next order correction in lambda, right? I can take that full expression from how lambda prime is written in terms of delta lambda and delta z. That is the full expression. In D equals 4, this goes away, right? Which means it's a marginal operator. And now we have to analyze the contribution of delta lambda and delta z. Happily for us, in lambda phi 4, right? And you might remember that we calculated the loops that contribute to delta z, right? The first correction is this. This is the field strength normalization for a scalar field in lambda phi 4. So it's this contribution, right? We calculated this loop, right? And this loop is just proportional to the mass. There's nothing proportional to momenta here. If you would write it like that, right? This term was 0 at this first order. So it didn't correct delta z. If you remember, in the counter term way of doing that, we concluded that delta z was 0, right? So this is a lot of videos ago. That's actually in the start of the course, so you might not remember. I'll put a link to it in the comments, right? In the description. So that means that delta z does not contribute to the first corrections did not change delta z, so that delta z is 0 at leading order, and that allows us to write these just as lambda plus delta lambda, right? And this delta lambda we calculated last video, right? We have seen that's the what I call zeta last video, right? Zeta is actually like that, right? Last video, when I integrated out phi hat, right? So lambda prime will be at this order, right? Lambda minus, and this is what we calculated. This is zeta is minus 3 lambda square, 16 pi square log of 1 over b for one step of size b, right? And then you see b is smaller than 1. That means this log is positive, right? It's smaller than 1 but bigger than 0. That means the log is positive. And then this minus here tells me that lambda prime slowly goes down, because remember, what? This is square, sorry. So lambda square is small because we're close to the perturbative limit. So this is much smaller than the scaling with b, right? It's now the log of b actually is also involved here. So it slowly goes down. So we can take a look at the renormalization flow, right? Let me just edit this. So now it's not c, but this dimension represents every other operator other than these two, right? Because these two are the only ones that are not irrelevant. Now we know that everyone here, right, with dimension bigger than the dimension of lambda, right, will bigger, the operator has dimension bigger. That means the coefficient has bigger negative dimensions of mass, so everyone else is irrelevant. And that means that they flow to 0 faster than lambda, because lambda is also flowing to small values, right? But now on a second order effect. That means that if I started a trajectory here, it's flowing towards the origin, right? Forget the mass for now, I mean in this plane, right? The lambda, everything else plane here. It's flowing really fast in that direction, but also in that other one. Since lambda flows slower than the other operators, it will look like that. Of course, in this direction, it flows straight to the fixed point, and this one also, right? And this is really asymptotic as you get close to the origin, right? Because the closer you get to the origin, the slower everything flows. So this is really asymptotically going to a free theory, right? And of course, the mass is the same we had before. Along the axis of the mass, the projection on the mass axis is always going up. So in this plane is doing something like that, right? And because nothing changes of the mass is still relevant, right? Sometimes it's called the triviality of lambda phi 4 in 4 dimensions, because if you try, this comes from the UV, right? This point is the UV of the theory. If you try to throw this point to infinity, again, you're trying to make your theories valid up to arbitrarily large cutoffs, then you have a lot of time to flow towards the infrared, and lambda flows to 0. So you say that lambda phi 4 theories are always trivial, too far away from their cutoff, because they will flow to free theories, right? But that doesn't mean that if your UV cutoff is finite and you're not that far away from it, that you don't have a useful lambda phi 4 theory. So there are many cases where you can use phi 4 theories in that case, right? Now let's look at the final option here, which is what happens if d is smaller than 4, which is the typical case when you're doing lambda phi 4 in solid state or condensed matter systems, right? Now you think of 3-dimensional systems, 2-dimensional systems, right? Remember, we are all Euclidean here, right? So in that case, right, lambda is now relevant, right? Lambda now grows with as you go away from the UV, right? So delta, again, I still can use this expression, right? Now I have a dependence on B, right? I can use the full expression for delta lambda that I got before. I just have to generalize for d dimensions. So my delta lambda now is, if you remember, the integral of zeta was minus 3 factorial lambda square, right? That's in the last video. We did d4k, now I want to do dk, so I can use for 3 or 2, right? Over 2 pi d, sorry, this is a d. This is integrated between b lambda and lambda, right? And you had a 1 over k square. That came from this diagram, right? With a double line here and here, right? This is where delta lambda comes from. Now, this is you can do the integral now in d dimensions. We did it in 4, but it's also finite integral. There's no complications here. It's just really just an integral. Right? One minus b d minus 4 d minus 4 lambda d minus 4. Now you could ask, why are you calculating delta lambda? Isn't this just dominated by that's far away? Isn't that just this behavior, right? And the thing is, now that this is relevant, this guy will grow and grow, right? And once it grows, eventually this term becomes important. So I'm calculating the most important correction, right? Which is delta lambda, right? Because of the same logic I use here, right? Delta z is even a higher order correction. So there's a point where it's still perturbative, but maybe this delta lambda starts to compensate for the scaling, right? And that's what we want to see. So now lambda prime is given by lambda minus delta lambda, actually plus delta lambda, but there's a minus here. So let me put this one here, try to coincide the minuses. And of course there's the scaling. The scaling is out here, right? So if this is too small, I have lambda 0. If this is too small, I can throw it away, and it's just lambda b d minus 4. But you see, there's a possibility that this is big enough, and let's see what happens, right? Now, the first contribution, lambda times b d minus 4, tells us that lambda is growing. The second one tells us it's going down, right? So what could happen, depending on the size of lambda, where the point where we begin, right, is that there is another point here. Let's call this Li, right? Where if lambda is still perturbative, but bigger than some critical value, where this wins over this, right? Because there are many factors here, right? Then lambda should decrease because of the minus sign right here, right? So it flows towards the left. If I am at a point where this wins, and that's for small lambda, right? Then lambda should grow away from the perturbative, fully perturbative region, right? I mean the zero coupling region. Let me put that in red because green is hard to see against white, right? And at some points here, of course, every line flows, because this is every order coupling, right? Every order Wilson coefficient, they're all flowing down there, assuming none of them also become relevant, right? And so intermediate curves, they're all flowing towards that point, right? So you can see that if I get there, I get stuck in that point. So this is another fixed point for my theory, right? This is a non-trivial now fixed point. It's a fixed point where the theory is flowing towards it, slower and slower as you get near that, because this coefficient is starting to be zero, right? And I can factor out a lambda here. Right here, I can solve this equation to see where this point is, right? But now lambda prime is becoming closer and closer to lambda, because I'm flowing slower and slower towards a non-trivial interacting fixed point. So I can have an interacting theory that doesn't change as I change scales now, because I found another fixed point. And of course, I can make these by changing the dimension, right? If I go into 4, and I compare this plot with this one, I should go back to this situation, right? And that means that this fixed point, as I go to D closer and closer to 4, it needs to move to the left until it coincides with the trivial one, right? Because that's the situation in the previous case, right? And so you can conclude from that if these points are not too far away from each other, so if I'm close to 4 dimensions, the behavior of the mass should be the same on both points, because they need to go to each other in that limit, right? So as long as I'm not too far away from the Gaussian fixed point, and that means not too far away from 4 dimensions, then these two masses, the behavior of the mass behaves like that in both points. Of course, if I go too far away from D equals 4, I need to analyze everything else, because even other operators can become relevant, and you have to be careful with that. Right? So you see that in some cases, even if you are within the perturbative or going close to the edge of the perturbative, what we would call the perturbative regions, then you can develop really interesting non-trivial fixed points. And that's one of the beautiful things with this group flow analysis, right? That you can find those very non-trivial theories. That's the memo for the day. See you next video.